Hi. Um, so in 1961, the avant-garde composer and philosopher Henry Flint proposed concept art, which was art where the material is concepts and not in the same way that, for instance, music has sound as its medium. And he was inspired in this by what he called structure art. This is stuff like fugues, total serial music, a lot of music where the intended purpose is to convey some kind of structure, and simultaneously by mathematics, but going beyond structure art, which he didn't like the structures, and he also didn't like it as music, and going beyond mathematics because he didn't like the idea of discovering theorems. He was a very out there philosopher. Um, there's what I would say some real examples of this arising from mathematics, going beyond discovering truth, and this would be the paradoxes of formal systems. The intention of something like naive set theory is to capture truth or, naive dependent type theory, but they're subject to inconsistencies that are beautiful and rigorous concepts, but you can't consider them true because they destroy the system that they were intended to use as their notion of truth. Um, so my goal with this is to create structure music inspired by the structures of these genuinely beautiful pieces of concept art. My aesthetic influences on this are Yannis Xenakis, less on the actual sounds of this, unlike the previous one, and more on the approach to developing this. He used a lot of mathematics in his composition, and I thought that was an interesting method. And he emphasized that not only should it have mathematical structure, it should have arbitrary choice as an element of the art. I'm also inspired by Catherine C. Hennicks, who was a composer, mathematician, and philosopher. She worked with a lot of relevant figures, including Henry Flint, Lamonte Young, the minimalist composer, Pandit Pran, the Indian classical musician. She taught logic at MIT. She worked with the Russian ultra-finitist, Alexander Asenin-Volpin. Very interesting figure. Her work, The Electric Harpsichord, is one of my favorite pieces. Um, and then in terms of some of the actual music in this, I'm inspired to some extent by techno, metal, jazz, and I'll talk more about that a little later. So Girard's paradox is defined in dependent type theory, and it's a form of the lambda calculus where types are allowed to depend not only on types, but also on terms. It basically eliminates the split between terms and types. There's a judgment of this term has this type, and types are simply the kinds of terms that can be the type assigned in that judgment. You don't need to understand all of these rules, but that's generally how that works. Girard's paradox appears in certain basically naive forms of dependent type theory. It's a variant on the Burali-Forti paradox of ordinals. Basically, it says that if you have a set of all ordinals, there's an ordinal corresponding to this set, and then that ordinal has to precede itself, which is impossible by the definition of ordinals. And the problematic feature of the type theory here is what's called type and type. If you look at this rule here, the type star is the type of types, and that is assigned itself as its own type. That's not consistent. Real type theories resolve this by using a stratified universe levels generally. When it doesn't have it, you get the paradox. It was developed by Girard using this theory of orders without torsion, extended by Thierry-Coquand to system U minus, which is a simpler version of it. And the proof term was simplified by Antonius J. Herkins. It's based on this notion of what he calls a powerful universe. You encode the power set of a type as the predicates on that type, and then a certain type in that is in a certain way isomorphic to the power set of its power set. This gets you the paradox. I'm doing this with a system that I call Soundproof that I've developed for the purpose. My goal is really only to translate this one term, but to be principled about it, I developed a system for translating arbitrary terms, which is easier really than trying to get each piece of the structure manually. So it translates a term from lambda pi, which is a tutorial implementation of dependently typed lambda calculus by Loch, McBride, and Schuster. It's bidirectionally typed de Bruijn indices. It's got type and type, and all of these are features that are intended to make it simpler to implement, and that means that it has Girard's paradox. I translate that into what I call a sound tree, and I'll discuss that going forward. And then it's turned into sound using the Rust library FunDSP, which is a library of composable combinators for digital signal processing pipelines. And the connectivity of these pipelines is checked at compile time. It uses basically compile time natural numbers, and the resolution of this ensures that it's all going to work and you don't have any dangling loose ends. So the big question is, if we're going to translate it into a sound tree, what exactly is the tree structure of a proof? So there's the natural deduction style, and that's a classic one, but we have the type theory proof term, so we don't really need that. It's unnecessary, but the visual layout is interesting and comes in later. The term structure, we just have the abstract syntax tree of the term. The problem with that is that when you get to a variable, bound variable 0, in this example, what exactly does that variable signify? That's really not clear. The importance of a variable depends on the specific type of the variable. So instead, we use the call tree of the type checker. Basically, I re-implemented the type checker and had it build up a sound tree as it checks and infers the type. And then this contains the full AST structure, because every term you have to check all of the types of the subterms to verify that it's valid. And for most terms, it just stops there. Once you know the types of all the subterms, the type of the term is obvious. But when you include variables, you have to verify that the type is valid, pulling that from the context. It's not in the AST, and so that adds that into the call tree of the type checker. This gets you a richer musical structure and better conveys the significance of things. So this is an example of some of the code from the type checker. You can see it at the top. It gets a tree and a type from inferring the type of the function being applied, verifies that that function is a pi type, that's the dependent function type, checks that the argument has the appropriate parameter type, and gets a tree out of that. And then it returns a combination of the result type of the application and a sound tree, which has the melody for the application node, and which also plays the trees for the functions and the argument. So the idea is that for a sound tree, each node variant in the AST is associated with a particular little sound. In this case, it's a melody, basically. And what we do is simultaneously, we give a duration to the root, we play that melody over that duration, and then the sound tree splits up that same duration among its children, and then plays the first child over the first portion of it, the second child over the second portion, and so on, and does this recursively so that you get the whole depth of it. And as things go deeper in the tree, we pitch them up. And if this is a spectrograph of the result for a fairly simple one, you can see it's got these sort of spiky structures, and the durations are longer as it's at the lower level. That corresponds to the structure of the sound tree. And here's an example. So here, this is the type theoretic power set. It annotates on the left here a lambda. The lambda has a body, which is the pi type arrow type, or T arrow type. T is the free variable. The free variable has type, and the output of this is also type. And then we annotate the whole thing with type arrow type, which is the pi type here on the right. Oh, I guess this would be an easier one to gesture to. And we synthesize this using FunDSP. This is an example of a FunDSP pipeline. And I'm just going to skim over this because I want to make sure I have time. So here's a little bit more complicated of a term. This is the powerful universe U, and it is being covered up by the meeting controls. If I can hide these. There we go. So here, for all x of type, that's the t here and the pi. It's a function which takes the power set of the power set of x and returns, or sorry, a function from the power set of x to x and returns an element of the power set of the power set of x, which is a type.
The parentheses there are not balanced.
Yes, they are. There's.
Oh, so they are.
Yes. Okay. And so there are several points of choice in this. The important ones, first, the division of time between the children of a particular node. If we do it evenly, so that, something with two children just splits it in half, this results in some really, really uneven sounds. For instance, in the paradox, we annotate that with the type false. If we did it evenly, half the time would be spent on the paradox, the whole thing of it, and the other half would be spent just on the type false, which is not a very interesting piece of music. If we divide it up based on size, if we do that raw, that ends up being too vague. Like, one of the key things that distinguishes between things at different levels, in addition to pitch, is how fast they're going. And if it's divided up purely based on size, all of the leaf nodes are playing at exactly the same speed. That doesn't work. So what we do is we weight with a fractional power, and we take the sum of the weights of all the children, and that to a fractional power. This compounds as it goes down, but then generally speaking, larger nodes will take longer, but it's relatively more balanced. We also, depth scaling, we use discrete octaves. It's basically the square root, because the depth can go up to like in the 20s, and we can't span 20 octaves. Square root divided by 2.5. And we also adjust the time characteristics of the note as we go up in the tree, basically changing the attack and decay so that it's got a little more of a twinkly sound as it gets deeper in the tree. But the most important question is, what sounds do we use for each node type? So first, the way that I had it set up was a sound generator. It was just using melodies associated with each tag. I extended this using a trait sound generator that basically signified anything that we could sequence out over an arbitrary duration. So audio clips with some stretching, this ran into issues because it just takes a really long time to stretch audio relative to any of this other stuff. I did some stuff with loops, stochastic musical textures. Those ran into some difficulties. It doesn't change speed very much. That's something that could be worked on potentially in future things, but I decided to ultimately use still basically melodies, but with more variance in rhythm and post-processing effects and so on. And one of the key things that I wanted to do with this was be able to experiment with a lot of different ways of presenting this. So I defined a trait called selector, which is basically a selector is a method of picking a sound for each AST variant. It can generate a sound tree for a term, but it also can have internal state, which it updates with each term that it sees as it goes through the type checker. So the idea is potentially the sound for a particular node in the tree can depend not just on that node itself, but on the sequence of parents that the selector saw as it went down the tree there. So there's a variety of these that I defined, but what I ended up doing was having the sequence of notes is determined by the AST variant of the node, but the variant of the parent of the node determines the rhythm, the synth instrument that it's using, and the post-processing effects that are put onto it. So it conveys both the specific node that it's at, but also what context it's in. So if you have a star that appears in the context of a pi type, that'll sound different than a star that's appearing in the context of a lambda, for instance. And here's an example of a bit more complicated of one. And you can see in green, I've highlighted the previous one, that's the powerful universe U, which is also that's this whole thing. And here it appears, you can see several times. So this presents the visuals of it. And here's a spectrogram of this. What this looks like. Sorry. One of the other questions is basically for the terms, should we normalize them or should we continue to have like annotations and unapplied applications and so on? So this is one that still has the non-normalized formula. Paradox. And you'll see that it gets quite complicated when you get to this. Okay. Future work for this, I'd like to incorporate the reduction behavior of the proof term. It doesn't normalize, so I would have to switch it to a small step evaluator, which is kind of tricky with the bidirectional typing, and I'm not sure how I would lay it out with respect to time. And I'd also like to experiment with some more stochastic textures and so on. Questions? Do I have time for questions?
Robert Carter says, yes,
Yep.
this unfortunately is you don't say that I want to ask a question. Ask the audience.
Probably a bit out of left field, but what are your thoughts on applying this type of methodology or some variation to listen to the SMP lib solve?
Well, I think you could try that. I think you would need to do something more complicated than lambda pi for that. And that is pretty far future work, I would say. But I think it could be interesting.
Some collaboration.
Okay. Yes?
Clearly, the complexity makes the sound interesting.
Mhm.
We've mentioned before, maybe bad proofs sound worse than good proofs. Do you find that paradoxes sound different than sensible proofs?
I have no idea, but I think the method of this would generally produce relatively similar sounds no matter what proofs you put into it. This is intended as a way to produce a piece of music based on one particular proof. So I didn't put any real effort into making it sound different for different proofs. Yes.
Thank you for the talk. Under the sort of higher sonic structure of the full Girard term, there's a persistent tone. What is that being generated?
Probably the annotation, which runs for the whole duration of it. And so if you have the melody that plays over the entire, the full one is like 40 minutes.
Yep.
If you have a melody that's playing for the entire 40 minutes, it's just going to sound like a drone at any particular moment of that. And it's a 4-note melody.
Yeah. I listened to the 40-minute version while programming rock and roll. And that undertone was something I was really curious about, because you could sort of parse out the melody with respect to the terms maybe a little bit, maybe I was making it up, but that under thing is something else. Yeah.
For those who have set conflict, can you tell us where to find the full 40-minute thing?
Oh, yes. It is at isdra.bandcamp.com. Free download.
Nice.
You can ask afterwards.
Yes.
1 second. I have one teacher's prerogative to ask you a question.
Yes.
The underlying melody that Roger was referring to, extended over time, has sort of echoes of the Cantus Firmus tradition and Renaissance era polyphony. Is this something you're familiar with?
No.
Okay, I shall take my music theory questions offline. And I think, Ricardo, are you all set, or do we have? Just that? Looks like another moment. There was one question.
So there was this subtree that appeared in multiple places in the big proof tree. Is this recognizable by ear? Do you feel like a theme that repeats? Or
The audio will go.
Sorry, I think I missed the start of your question
yes,
because I was.
the green subtree that appeared in multiple places.
Oh, the